if you have two phases and a solid, basically you have three phases, then from your own observations, if you take a capillary tube with water and air in there, you know that there are three interfaces. There is a solid phase, then there is an alpha phase, and then I phase back there, beta phase, and they form interfaces with each other. And the three interfaces come together on a contact line or a common line. So you could, strictly speaking, say phase alpha never sees phase beta. It only sees an alpha-beta interface. It doesn't see beta phase because it's separated by alpha-beta interface. So, and the same for other phases. And the three interfaces come together on a common line. So the interfaces don't see each other. They see only a common line. And a common line is something of potentially of its own entity, on its own nature. The same way interface is something of its own nature. And this goes back all to the molecular picture we talked about before, that we say, look, if you have here molecules of water, water is here, blue, and we know that from what we discussed the last couple of days, that everything is determined by molecular interactions. What kind of molecules you have, what is their interaction, how they internal forces are, for example, that determines the constitution of the material. That what makes water different from air or from oil. So we saw that when you have a water and salt, for example, that you get different behavior than if you had only water molecules. You get different equations even as a result. So, okay, so these are air molecules. So I would say, you remember, a material point is at the macro scale is a point in a space, mathematical point, where around this mathematical point we say there are many particles, and the average properties of those particles are assigned to that material point. So at any material mathematical point, and any mathematical point, we basically saying that one type of molecule exists around it. And here is blue, here is, say, brown. And that determines their composition. As we approach the interface, at some point, molecules of, say, brown start to see molecules of blue. And then, now, other interaction forces come into play. And now there would be different behavior. You must expect a different behavior. What is water and what is air, determined by its molecules. Now you have a mix of water and air. Different behavior must be expected. So that's why interfaces are important. So I define in a minute formally how we divide the space. We say, okay, we have this molecule or that molecule, the phase or interface. But I hope you realize the fact that, by the way, I'm here assuming that the two phases absolutely don't mix, just for the sake of simplicity. You can then relax that. But for now, I say it's not possible for any of these to come here, any of these go there, except for a transition zone where they will be over a region. You will have both molecules present in this region. So it would be a molecularly thick region where, so you have like that, where both are present. And then like that. Okay? Good. So we say, if we now have a system M, and it has, again, point masses, and they belong to, actually, to 3 immiscible phases, but if we take solid, which we would like to do that, and the particle, as we just did it for the case of 2-component system, we assign not only an ordinal number to it, but also an indicator alpha. So this alpha could be solid, could be wedding phase, could be non-wedding phase. They have a mass and a position vector. And I don't know what happened, but I changed this last night. So this is a position vector alpha. We follow these particles. A position vector, and then this changes with time, and so that's how we define velocity. We had all of this for a single component medium. We just repeat it here, and we do it for each phase separately. Then we say we define a particle to belong to phase alpha, a particle pi alpha, if in a sphere of radius delta around it, only alpha particles exist. Then we are in alpha phase. The same holds for the beta phase. And then there is a transition region, an interface region. In that region, if you have a radius, a sphere of radius delta, in that sphere we will find particles of both. So now alpha particles that are in such a sphere and beta particles that are in this sphere, they are not alpha particles anymore, they are not beta particles anymore, they are alpha beta particles. They belong to the interface. So we label them separately, and we denote them by pi alpha beta. So that means, actually, strictly speaking, in the case of two-phase flow in a solid, the whole space is divided into 6 entities. The 3 phases, 3 interfaces. Actually divided into 7 entities. The common line. Because the common line is where within a sphere delta, a sphere of radius of delta, you find all 3 phase particles there. Okay? Now then, the rest is actually more or less what we did for single component, and this morning for 2 component is just repeated for the phases, the interfaces, and even the common line. We say that these particles exert force on each other. It doesn't matter what kind it is, they have this, and there is always this second law of Newton says that they are opposite of each other, and there is an external force exerted, and this is bi alpha or bi alpha beta, or for that matter, bi alpha beta gamma for the common line. Okay, now then the conservation of mass says that individual particles of mass mi alpha, this mass is constant. The number of molecules of alpha molecules are constant, but this also applies to the alpha molecules that belong to the interface. That is constant, not each in the alpha phase itself. Which means that if you now write the balance of mass, derive it the way we derived it, you have to derive it for a decaying material, because this alpha phase will lose particles into alpha beta domain, and the other way around, can gain particles from alpha beta domain. So it's a decaying alpha phase. But the total number, of course, remains constant.
Can it not get particles from the common line?
The phases don't get particles from the common line. That is correct. The phases get, the interfaces can get particles from the common line because the phases don't see the common line.
Okay.
They only see the interfaces. Yeah, that's very good. I mean, these are, yeah, at the end it doesn't matter, but if you really want to do it properly, then you have to take all these into account. Clearly make this distinction. And then we write for each particle pi alpha the second law of Newton, and that says that, is this the first law?
No, this is the second.
This is
the one you mentioned before was the third.
That was the third law. I'm sorry, yeah. The second law, yeah. It's some things you have said for ages, and then it is imprinted there, and then you start, what was it first, what was it second? I don't know, those who are Muslims and pray, I don't do that anymore, but I used to pray, and then you have to, for example, a given, after lunch, you have to pray 4 times after each other. There are 4 set up verses. And then after the second one, I say, was it the first one, second one, was it the third one? Oh my God, and it was always a hassle. So hopefully there is an app now that it will keep the track of it for you.
Is that why people have beads to count?
Yeah, actually, maybe that's why. I don't know. Yeah, I it was terrible because the idea is that as you are praying, you will be concentrated toward God, and then you forget. Okay, what was it now? Second one or the third one? Anyway, so it's the second law, and then it says that the momentum change is because of forces that this particle received from other alpha particles, and also from other alpha beta particles. Sorry, from other from the alpha beta particles. Now, the difference between what I just showed you with the components is that this now exists only near the interface. This is a boundary force, actually, only at the interface. And the reason I have this second summation, because alpha phase could be in contact with the solid or with the other fluid. So there are 2 phases that are affecting alpha phase. And so each phase always has at least 2 interfaces around it. So that is the 2 interfaces. You sum over them. But this only is present at the boundary of the phase. And then you have the external force. Okay, so that's the, and you write this for all 3 phases separately. And then we define mass density, which is now the sum over all alpha particles. And now please remember that this will be done only for the alpha phase. So the alpha particles that are in alpha beta are not included here, of course. And the same for the other phases we define. And the momentum is defined in the same way. And I think I have a slide for the, just, do I have, yeah. Yeah, I have a slide separate for the alpha beta interfaces. So this is for the alpha phases, for the bulk phases, let's say, momentum is defined, and then we can derive the mass balance taking the derivative of this, but not now noting that this n alpha is not constant in time. Some of these particles go to the interfaces and come back. And because of that, we have to use the procedure for a decaying material. And we get, therefore, a mass balance where there is an exchange of mass between alpha particles, the alpha phase, and the alpha beta interfaces. I noticed that I'm also missing here the summation sign for the beta. So there are two interfaces. Now this alpha density that's defined here, this is mass per unit volume of space. And we have to, if you want to work with the real densities, then we should define this as volume fraction times the mass of the phase being mass per volume, its own volume, not volume of space. And the volume fraction, as you know, you can also write it as porosity times saturation. Okay. Now, then the momentum balance, we did what we had done before. We take each term multiplied by psi and then sum over all alpha particles. Once again, these are particles that are in the bulk phase, not in the interface. And we get, basically write that. And then we do the trick that we put psi inside the time derivative. That will gives us a term related to d psi dt. And that we use the chain rule of differentiation. Now, this we simply identify as a force within the alpha phase. This is a force that is only at the boundary of the alpha phase, and this is a body force. So, those are now defined here. And that gives us a momentum balance that is, again, here I'm using minus sign. I don't know what's going on. And because this is of the same nature as this, and this was part of it, and I put it to the other side, so there's a minus sign there. Okay, and this one, which is within the phase itself, again, I assume to be related divergence of a stress tensor for the alpha phase, and then I put that together with D, and that gives me the stress tensor within the alpha phase. And this force remains, it was a boundary force, but actually, because I do the averaging over the whole domain, the whole space, this boundary force is everywhere. So it's also a body force for the alpha phase. And because my REV is now includes many, many pores and many, many interfaces. Average over everything. The psi distribution was over the whole space. So this is everywhere, except that it existed only in the alpha beta boundaries. Okay, so this is now actually very similar to what we had for a component momentum balance. Okay, now for the interface, we say that the mass of individual pi alpha particle is either mi alpha or mi beta, and that's constant. And the total numbers are not constant. So the total numbers come and go, and so we have to take that into account. And the momentum conservation for an alpha beta particle, this is the cut and paste, it's not really doing a good job. Is that beta here? So that the momentum is because of forces within the interface zone. So the alpha beta particles are hitting each other, is exerting forces on each other, but also these alpha beta particles of the interface see alpha phase on one side and beta phase on the other side, and they also have interaction forces. These are these two here, and there is an external force as well.
And you promised that they would see the common line.
Oh yes, yes, you're right. Absolutely right. So there is actually I should have, and this is, there's no sigma. There's only one common line, Yeah, so these are the things I was hoping that you will say, oh yeah, I forgot that. No, forgot, I did this intentionally. So this is an alpha beta with alpha beta gamma. There is that force too. That has to be done. Very good. I have to really clean up this, and then today I'm going to send you some of these PDF files. I don't have your email addresses, so Marie-Laure.com
You can please send it
today.
to Marie-Laure, and she.
Yeah, so
and then you tell her what you prefer, whether we should put it open or not.
Oh, it can be
I
open,
think
no
so,
problem.
Yeah.
Yeah.
You put it on our website then.
Sure,
Yeah.
no problem. Yes, is she coming back today or tomorrow?
End of
Monday.
Oh, I thought end of this week, but
Yeah.
Or maybe Friday, yeah, no, tomorrow.
I thought she said that this week, and then if anyone else has the list of participants, I can send it to you. Otherwise, I know she has. Okay, so
Yeah.
and now once again, and for the same as we had an REB for alpha phases, we have for alpha beta phases, we define a mass density. Maybe I didn't stress enough. This is, I am not developing equations for an interface domain in the sense that my mathematical points are not living on the interface only. The mathematical points are everywhere in the space. And at that mathematical point, I am looking, let's talk in terms of REV, not inside, but in terms of REV. At any mathematical point, I have an REV. And within that REV, I identify all these alpha beta particles, and I sum all of them. So I'm not developing a Gibbsian notion of interface, where it says, okay, here is alpha phase, there is beta phase, and that's the interface. I have alpha phase everywhere, beta phase everywhere, alpha beta interface everywhere.
So you're not using these psi functions to define, because before you said an interface particle of type alpha doesn't see only alpha and type beta doesn't only see beta. So a product of psi functions could define what is non-zero at the interface, but you don't do that in that way, do you?
I put it in here. So this psi has, at any given mathematical point x, I see that this should be a small x. At a given mathematical point x, this psi has its maximum value, and then it dies off. Then I say, I look at the whole space, at any other, if a particle is found there, is it an alpha beta particle? Then it's non-zero.
But I mean, you in principle could define something like a psi alpha and a psi beta.
Absolutely.
And then you take the product to make sure that.
That is correct. That's how we did it with Murdoch and Murdoch.
Okay.
And but it
No,
just makes it.
No, okay.
Indeed, that is the correct way if you want to do it mathematically.
Because this is not an excess.
This is not an
the
excess.
total amount of mass in a region which has the thickness delta, which was the distance over which you want the particles to see each other.
Exactly.
Yeah.
Yeah. But now what he's saying is that I should have potentially add another distribution function that will say, then I didn't need to put alpha beta here.
Yeah.
That distribution function will tell me, oh, is this particle an alpha particle or beta particle or alpha beta particle? That's how we did it with Murdoch.
That will also give you a finite region, so that doesn't make much of a difference.
No, it doesn't make any difference. So I thought, instead of putting that, I just put this indicator here. But what, maybe I make a digression here. What Dick is mentioned is the following. Look, if you, let's see, can I get a white screen? If you have an interface So here's the interface. And you want to model this in the sense of what I call porous scale model, at the porous scale. So at the porous scale, actually, you know what? I could have used the graph I had at the very beginning. Yeah, here. So at the porous scale, if I say I go from molecular to the porous scale, then I have here this particular phase. I can define density field. Let's take density. You can do it for anything else. Let's say density. So there's a density field defined here. So, and if it is homogeneous, density is constant because the number of molecules, the brown molecules. So if I plot that here, density as a function of number of molecules, so this is constant because its air is small until I reach here, and now I see water molecules, so it is going to increase, and now it gives you the density of water. Okay, but this region is indeed of molecular dimensions. If you want to solve Navier-Stokes equations, you cannot possibly model this with Navier-Stokes equation, because Navier-Stokes equation are valid here, Here is a different animal. So what do we do usually? We say, okay, you know what? This is a sharp interface.
Yeah, but I mean, this interface you have depends on your choice of delta. So the thickness of that interface is delta.
That's definitely the case.
And
So,
of course, you can then subsequently try and make it sharp, but you haven't been doing that yet.
no, so if I really do want to do, as I said, porous scale modeling, like Navier-Stokes equation, I have to make it sharp. I have to assume here is this phase, here is that phase, separated by a surface of discontinuity. So here I put an interface somewhere, okay? And let's put that. Let's take the color red, and I put the interface here. So what does it mean? That means up to here, I have water, and up to here, so on one side of the interface I have air, on this side I have water. Well, strictly speaking, I am not conserving mass, because the real mass density is this. I've replaced it with red. Now here with I looks like that this area is the same as that area. Then okay, maybe I've conserved it. But how about if I chose to be here? Now the mass density of water is extended there and the air only here. So now you have a lot more mass assigned to this whole domain than what is really there. So Gibbs said, oh, that's not the problem. We call an excess mass. Excess mass is the difference between these straight lines and the curved one, and we assign that to the interface. That's called excess mass. And actually, for that matter, any other quantity, momentum, and so forth, and they call it excess quantities. And in fact, I will show you later, there are balance laws that give you balance law here, momentum and mass, balance of momentum mass here, and then balance for the singular interface. The problem is that excess mass could be even negative. You can have negative excess mass because of, depends on where you put this. Here, in fact, you must have negative for this one because you assign too much. So that interface has to have a negative mass so that the balance is okay. That is a construct. Why not? What's wrong with negative mass? We can do it, and there are equations, we solve it, and that can be done. But the approach I present here, I'm not doing this. What I do, as Dick said, I have a large REV, and in that REV, I say, okay, there are alpha particles, beta particles, alpha beta particles. They are finite number, finite mass, and I add them all together and I get this, therefore, here, I get this mass density. This is a finite mass density. It's not, doesn't need to be negative. Is that clear?
It cannot be negative.
Cannot be negative. Exactly. Yeah, I'm not a mathematician, you can tell. Not understand quite. Okay, so this is now mass per volume of a space. Remember, psi covers the whole space. It's per volume of a space, but you can imagine that that interface has a mass per area. That if you have surfactants, that mass per area may change, but if you don't have surfactants, temperatures don't change, then mass per area is constant, the same way that the phase density could be constant. So it's better to break it into area per area multiplied by mass per area. So that A alpha beta is area of all the alpha beta regions divided by volume of a space. Okay? So I hope you notice that I'm not really throwing term. I follow this procedure. At this stage, I can choose to work with this. And in fact, you can do that. Go through the whole entropy inequality, and you will see at some point you will have to introduce this area. But I do this decomposition here. Why not? This is mass per. This is the real mass density, and that is the part that relates to what part of domain is space is being occupied by that mass density. Now, the same way we define a momentum balance, a momentum term, average momentum for the interface, which again we can write it as A alpha beta, gamma alpha beta times the average velocity of interface. And if we now go through the derivation of mass balance for a decaying material, this particular material will lose mass to the alpha side or to the beta side. Therefore, we have to have these extra exchange terms. And here I really should put, this is A alpha beta gamma alpha beta. So I remind you that this should be replaced by those terms. And these are exchange of mass with the two neighboring phases. Okay. And we get also a momentum balance for that interface, which is these inertial terms. The minus sign is right. And this is the deviatoric momentum exchange within the alpha beta interface. This is the force the alpha beta particles exert on each other. This is the force that alpha beta particles exchange with the neighboring phases and the outside world. And we define again this to be a divergence of some sort of S prime alpha, some tensor. We put that tensor add to this tensor add to D, and that gives me a interfacial stress tensor. And these are the forces with the neighboring domains. Too many equations, but all the same format. It looks the same. It's just always something being added to it. Now this the repetition of all those now written for the solid phase separately, for the fluid phase separately, and for the interfaces separately. I haven't given one for the common line. I could do that. In fact, the interaction force, this was also missing here. You didn't catch it. There is an exchange of mass between the interface and the common line. Yeah. Okay. Then there are the momentum balance equations for the bulk phases and for the interface. So again here, and then the interface exchanges mass, exchanges momentum with the neighboring phases and with the common line. There is conservation of energy. No, nothing special about this, just repetition of that. Then we write the balance of entropy. Again, it has the same form as we had it. Time rate of change of internal entropy, flux of it, external supply, and the exchange of entropy with the neighboring phases. You can also add with the common line, and then there is not equal to 0, but some production rate. And for the interface, this for the interface we have it here, is with the common line. And then the restrictions are that all the mass exchange terms between the three interfaces and the common line must be 0. You could assign momentum to the common line, mass to the common line. Then we get yet another set of mass balance and momentum balance, energy balance for the common line. Here I assume that the common line is massless. It's only a interaction line. Now then this sum of all the interaction forces between interface and common line is 0, energy excitation, and the sum of the entropy exchange terms is non-negative. The second law says that the total production of net production entropy for the whole system, and that is for the phases and for the interfaces, this sum, the three phases, the three interfaces must be non-negative. The common line doesn't have entropy because we didn't assign to it. Now we introduced the Helmholtz free energy as we had previously, and then if we now put these lambdas here, you remember? These lambdas for phases, lambdas for interfaces, we get this nice equation. I'm not showing this.
The fact that the common line has no entropy does not mean that it does not produce entropy.
Okay. Yeah, he just tries to make it more life difficult for you. He wants more equations here. You're not making yourself popular. You have been complaining there are too many equations. But you're absolutely right. That is absolutely true. But you know, that is here, Dick, because the exchange of entropy between the three interfaces is not 0.
Sure.
Is non-zero. That means, indeed, the common line
can produce
entropy. That's correct, yes. So, yeah, now this is not the equation I'm showing to impress you, because this is only one page. I have another one which is 3-4 pages. That will impress. Yeah, what is the composition of this? It's really, you have seen individual terms yesterday for a single phase, like solid or fluid. There is a rate of change of energy, Helmholtz energy with time, and then plus entropy times rate of change of temperature. You write this for three interfaces. You write it for the three phases, for the three interfaces. Then there is a term related to the heat vector multiplying the temperature gradient. Now you have it here for the three phases and for the three interfaces. Potentially interfaces and phases all have different temperatures. Then there is a stress tensor multiplying the deformation rate tensor for the three phases, for the three interfaces, and all these other extra terms relate to the exchange of momentum, mass, and energy. They appear here. They also play a role in production of entropy, those exchanges. Okay, so now I have completed my conservation laws and the second law, and it's time to go and develop the constitutive equations. We can do that again following what I did yesterday. Start with the axiom of causality. It says, okay, what are the measurables in this system? These are causes. Now, solid motion, the wedding phase motion, non-wedding phase motion, the motion of the three interfaces, the density of the phases, the temperature of the three phases. We have porosity, we have saturation, and then mass density of the three phases. We have interfacial area. So the same way the phases have a geometrical representation here, these are epsilon and saturation. The same way the three interfaces have this representation. And then at any given material point, this is related to heterogeneity and time. So these are possible things. And these are, then we say, the axiom of, is missing here, axiom of determinism says that all the other thermodynamic quantities like energies, entropies, stress tensors, heat vectors, exchange of forces, exchange of mass, exchange of energy, they are functions of these, of all points of space, all past times. Now, this is the most general constitutive equation you can write.
And why do you not use the length of the common line?
I don't think if we do not assign anything, I don't have length of common line appearing in my conservation equations because I didn't assign any property to it. Yeah. It's just a, in Dutch they say doorgeven, to pass over. So it doesn't play a role.
So there is no need for the common line to stretch or become smaller. Yeah, no, you have no line tension.
That is correct. There is no line tension. Absolutely. So if you, and it's not, in this context, in this approach, it's not possible to say, I assign tension to the common line only. It's either everything or nothing. It wouldn't be nice if you say, okay, I don't care about the mass of the common line, I just say there is tension there.
Now, if you have tension, you also have Helmholtz energy, for instance.
Then you have to have everything assigned there. And Helmholtz energy, now then it should be per, because all of these are working with intensive quantities. Yeah, so if that means Helmholtz energy per unit what? Length. Okay, then length. So that's why it's not here, and I don't think, if it was in my conservation laws, then I had to put it correct. So function, then I go through, there it is, axiom of. And these are independent functions of these variables. And then axiom of a smooth neighborhood says that, yeah, not all points of a space, only neighboring points. So that means the motion at the current point and the gradient of motion. Velocity, current point, the gradient. Everything, we can add a gradient or more, higher orders. It's possible. And then the axiom of smooth memory says not all past times, but only the current time. And then the time derivative of the motion and time derivative of all the other things. I haven't listed them here. Now, as you know, the gradient of motion is related to a strain tensor. The time derivative is the velocity of motion. The derivative of velocity is the deformation rate tensor. Now then we say, yeah, but these are not objective, so we go to the axiom of objectivity, and you say, yeah, this is a spatial coordinate. Cannot, it's not objective, it must go, t must go. Velocities individually cannot appear, but we can have relative velocities. So velocity of phases with respect to solid, interfaces with respect to phases, and so forth, and that can be done there. And then we say, okay, then axiom of admissibility. These constitutive equations must not violate the balance laws and the entropy inequality. And then that's what we will do. So these are functions of these. This is the full list of independent variables. Densities of phases and interfaces, velocity differences between phases and solid, interfaces and solid, the strain tensor for the solid, temperature of each phase, gradient of interfaces and their gradient, porosity is gradient, saturation is gradient, and interfacial area and its gradient. They must be a function of these. I think I'm going to stop here because there is something related to the time rate of change of saturation and area and porosity that I have to explain that separately, and I think this is enough for today. So, thank you very much. You have any questions?
I had one on the page with a multiple equation.
Okay.
Oh, did
You didn't know there are people who make the...
When you have this this S there, then it's stress tensors for the surface. You have this A font, but when you introduced it, I thought you did it
Oh,
the
yeah,
same
you're
way.
right. Absolutely right. That's correct. Very, accurate. Be able to see it. No, that is true. I must say this is coming from a written type text. I did sort of camera, and so that doesn't correspond. I must change that really. So what you're saying is that here, here there is no area. Yeah, that is correct. The same holds for the for the stress tensor of phases. In papers, what I have done is to say the stress tensor of a phase which acts on a imaginary surface, but that imaginary surface, only part of it is phase alpha. A good part of it is the solid phase and the other phase. Therefore, the truly intrinsic stress tensor is this should be broken into porosity volume fraction times the intrinsic stress tensor. And the same for the interfaces, that the truly interfacial stresses could be defined per unit area. This is per unit area of space. So you multiply this instead by interfacial area. Very good. And that's what indeed appears here. And you don't need to do that. At the end, you will come. Actually, so here, you mean this equation? Yeah, it's in here. Yeah. So if you recall, I didn't do this yesterday for the porous media. I had simply a stress tensor without multiplying by porosity. But what I found at the end was that the stress tensor for fluid, this is what I did yesterday, single phase flow porous media, was equal to minus epsilon PF. So epsilon came out by itself. So I could have potentially, in my balance laws, put epsilon here. And then that would have been intrinsic stress tensor and would have been equal to the pressure. Yeah, it will, none of these, they seem arbitrary, but actually will come. One of the other examples is that in the energy equation and in the when I went from molecular picture to the macro scale. Let's go back, please bear with me here. This D, I define the stress tensor to be this T prime, this one, minus D. And that gives me a plus sign here. I could have defined this minus plus T, why not? As admissible. That gives me a minus sign here. No problem. You can put this through. At the end, when, for example, you get Navier-Stokes equation, you will find that this T is not equal to mu times deformation rate tensor, is minus mu times deformation rate tensor. So the sign at the end will come out correct, no matter what you choose here. So none of this, it seems that there is some arbitrariness, but in fact, the choice you make will have an effect that later on will be the same. I really like that. Okay, then we will meet tomorrow. But please feel free to come to my office if there is some explanation you want. If some of it goes too fast, I'll be more than happy to go with you over details.